Hey and welcome. Today I'm going to talk about the Abaqus PRF model, also called the Parallel Rheological Framework model. The Abaqus PRF model has been around now for a number of years, and a lot of people are still confused about how to use it. It's a very versatile model with a lot of different features in it, and I think that can cause a little bit of confusion for some people. So what I'm going to do today is talk about how this model works, how you can use it, and how you calibrate it using the Mcalibration software. So the PRF model consists of a number of parallel networks, as you can see in this image here. You can specify how many networks you like. Each of these networks are represented using a hyperelastic spring and a viscoelastic dashpot. The theory behind this model is based on some work that I did a long time ago on the parallel network model. And I'm also mentioned frequently in the references in the Abaqus manual because of the work that I did for the PN model. The PRF model needs to have the same hyperelastic type of spring in each network. So you specify at one time what type of hyperelastic network you like, and then you also specify the type of viscoelastic viscoplastic flow you like for each of these networks. And then you can specify slightly different parameters for the different networks as well. You can include Mullin's damage if you like, and you can also include pure plasticity. But typically plasticity isn't that all that useful for the materials that are well characterized using the PRF model. So that's not something that I typically recommend or use. It's interesting though that when you specify the hyperelastic network, you only specify all the parameters for one of the networks, and the other networks are represented using a factor. It's like x times stiffer. For the next network, or the second one is then some other factor times the first network. So it's a way to reduce the number of parameters that needs to be specified. But that, of course, can have a little bit of limitations in the predictive capability because of that constraint on the model framework. The key problem that people have with the PRF model is the flow elements. There are a number of different flow elements you can select from. Here's the first one that I typically recommend, which is the power law strain hardening equation. And this is the creep equation. The rate of viscoelastic creep is on the left-hand side. And it's a complicated equation on the right. The key here is to remember that Q tilde in Abaqus nomenclature is the shear stress. And Q0 is the material parameter, P is the pressure, and this is the creep strain magnitude. This is actually a pretty good representation. It's a pretty good equation, and this is the one of the two that I recommend that you use if you're attempting to use the PRF model in your own finite element simulations. But as I mentioned, there are a number of other ones supported as well. Another one is the strain hardening model. This is one of the earlier ones that Abaqus supported for the PRF model. It looks kind of similar, but it's actually not a good model to use. You should not use the strain hardening version of the flow element here. You can see that this will cause problems because simply Q is the shear stress. You raise that to a power n. And n is typically of the order of 10 or so, perhaps even higher, that power exponential. A is a parameter that is a prefactor that needs to be such that you get either a no creep or relatively high creep as the stress reaches a value of Q tilde. So to demonstrate the problem, what can happen if you have a situation like that, I'm going to open up a little calculator here, make my window a little smaller. So if Q, if you use SI units, some people use that, of course. So SI units, if you have 10 megapascals, 10e6, and the power exponent n is 10, then A should be approximately 1 divided by this. So the parameter A would be 1 10 to the minus 70, which is a ridiculous floating point number, clearly not a good thing. Also, the A parameter has very weird units. So I say don't use it, bad idea. there are certainly better choices than that. Similarly, Abaqus supports something called the hyperbolic sine. In theory, this is an interesting idea, but again, it's implemented poorly. They have the Q factor and a pre-exponent B here. It's not going to be as crazy in terms of the values for the parameter, but it's not a good idea to use this one either. I typically don't recommend it. Don't go for it unless you have very specific reasons to use that one. The last one is the Bergstrom-Boyce version of the flow element. This is the model that I developed. Bergstrom is me, and Boyce was my advisor at MIT. And this is a pretty good representation too. This works very well for elastomeric materials, very specific functional dependence that gives you the correct response during both loading and unloading. So in summary, I would use the power law strain hardening equations typically for thermoplastics. I use the Bergstrom-Boyce type flow equation for rubber-like materials. And that would give you pretty far in terms of modeling. Another rule of thumb is that I would use 2 networks if you're working with rubber-like materials, and 3 networks when you're working with thermoplastic, stiffer polymers, basically, or thermosets for that matter. So that's what I would recommend. Let's show you a little bit more practically how this would work in real life. So I have experimental data that we talked about in some of my other tutorials. So I is going to open up one file here that I have. It's a polyether ether ketone peak material that's tested at 4 different temperatures. And I'm going to show you how you can calibrate this type of material model. I is going to open up Mcalibration. I'm going to open up my saved file to save time. So here it is. I'm going to go to the right folder. I'm going to open this file. So in this case, you can see that this Mcalibration file has 4 load cases corresponding to 2 tension tests and 2 compression tests. There are 2 different strain rates. I also, and when I calibrated this material model, I activated a Poisson's ratio load case, just like I demonstrated in some of my other tutorials on peak. What you do here to use this PRF model is very simple. You just go to Set Material Model. You scroll down to the section under Abaqus, and you see that under here there are a number of PRF options available, 2 network, 3 network, 4 network versions with different flow type elements. They're all hard-coded to use the Yo hyperelastic model, which is one of my favorites. It's easy to use and it's robust and therefore a good choice for almost all polymers. It's highlighted in yellow here the 2 kinds of options that I recommend, unless you have very specific reasons. Otherwise, I would pick either the 2 network Yo power, if it's a rubber-like material, perhaps also the BB model as I mentioned earlier, or the 3 network Yo power. So in this calibration, this is a stiff thermoplastic material. So I would recommend the 3 network PRF Yo power version of it. We talked about the equations. So you would select that, you would then run calibration, and then after a little bit you will get the results. So here are the calibrated results, the best fit you can get with this model to the room temperature stress strain prediction of this polyether ether ketone material. It looks pretty decent. It does good at predicting the different strain rates, relatively okay with tension and compression, unloading. There is a difference here though, that it doesn't handle the details as well, particularly the difference in softening after yielding that we see here, compare model and experiments. That's a weakness of this particular PRF model. It doesn't do that so well, but overall it's reasonably okay. So I will now export this model, because in the end I will show you how you can combine these calibrations at the different temperatures into a single temperature dependent PRF model. So I'm going to export this. The key is to export it as an Abaqus INP file here. So I save that. I'm going to save it. And there it is. I'm going to repeat this procedure for my other temperatures. And I have already calibrated these to save a little time. So I'm going to, Poisson's ratio is turned off. I run this once and we'll see what it looks like. This is a slightly higher temperature. And the predictions look similar in accuracy. The error is about 16%, which is not that bad, but it's not that great either. Overall, it's a little bit off here. but it's certainly useful for many cases, I would say. So I'm going to export this one too to an Abaqus IMP file and save it in the same directory. And then we go back to Mcalibration and we open up the third one. I'm going with the third one here, and we will run this once. And here it is. This one is one of the weaker ones in terms of the response. Experimentally, it's much sharper here than the prediction is, but overall, the fit is not all that bad. It's a 13% error. So, but that's the best I could do with this particular material model. I'm going to export this as well to a file, and there it is. And then we'll do the last one. This is the highest temperature. You'll see at this high temperature, the response is quite different. It's a much more gradual rollover. It's not a very strict, abrupt yielding response at this temperature. So you can still use the tree network representation here, and the fit is slightly better now because it matches the data a little bit better at this temperature than the other temperatures. I'm just going to export this one to a file and say OK. So if you want to simulate a component made of peak this particular thermoplastic at the temperature, this is 423 Kelvin, you could use this material model that was exported here, as you can see. It has hyperelastic, viscoelastic, nonlinear, and all that stuff. So what I want to demonstrate next, though, is, okay, so say you want to simulate a component that may be exposed to different temperatures. Can we combine these type of calibrations into a temperature-dependent model? And the answer is yes, and I will show you how you can do that. So here's our basic file. It's going to open a new calibration window, and I guess I can close the old one. Then I'm going to go to calibrate. So here's a new feature that's available in the upcoming release. To combine these files that have been exported, I go to Abaqus models, I go to template, and I go to temperature-dependent PRF. So I click on this one, and it's asked me to select multiple IMP files. So I'm going to select the files that we just exported. It's important that they have in file name that can be sorted by temperature, because they're imported in the order that are listed here. So I click OK. And here's our template for the temperature-dependent PRF model. We can do this by hand, of course, too, but it's very convenient to do it this way. Hyperelastic component, and here's the temperature. You see that the temperature is specified as a variable in Mcalibration language. So you can specify the temperature using variables if you read the format help here, but that's not something I'm focused on right now. I'm going to say OK. I'm just going to specify these to be the temperatures that we have. So this would be 296, this is 373, this is 423, and this is 473. So these are the 4 temperatures. Now the material model is done. We can export it to a file, and we can use it any way we like, and it will be a temperature-dependent PRF model. I'm just going to demonstrate how this would work by running a test case within Mcalibration. So I'm going to add a virtual experiment. I'm going to do uniaxial tension to an engineering strain of 0.5. Here's the temperature. I'm just going to keep it 293. Why not? I save OK. And then I'm going to just run it. So when I click run once here, Mcalibration will launch a Abaqus simulation for us, and we will wait and see it finish. It should finish in a few seconds. It takes a little bit for Abaqus to pull the license, but once that's done, it should be able to run properly. And here it is. I was a little afraid that they wouldn't run because I didn't see any files, but here they are. We'll see that it goes up. It has restrict yielding at this point because this is a relatively low temperature, and then it goes out all the way there. So this is how you can demonstrate and check it within Mcalibration if you like. And that's kind of all there is to this material model. You can use it just like I demonstrated. You can calibrate it to the experimental data that you have. A final thing to mention is the accuracy of this model. So I summarized that in this table here. You see that these are the 4 temperatures that we were looking at. This is for polyether ethyl ketone again. The PRF model accuracy, error in percent, on average for all the temperatures that we had data for was 12.6%. And just for fun, I also included data for the TNV model, which is another model that I talked about in one of my previous videos. The error for the TNV model is lower. It has about 37% more accurate predictions for this peak material. So those are two good choices though for peak if you're interested. So thank you for watching. I hope you enjoyed this video and let me know if you have any questions.